let's continue our tutorials. So I wanted to add one more problem about the first order linear equations. So consider situation we are looking for the function u of x1, x2, t such that equals u of xt, x in R2, t positive, and it satisfies the following equation. Let me write it. Du dt plus x2 du dx1 plus x1 du dx2 equals 0. And initial condition u of x1, x2, 0 equals, say, f of x1, x2. Now, after we solve equation, in general, we can substitute any f which we have. So, how to imagine it? It is x1, x2, t. So this is the x1, x2 plane, x plane. Yes. Here we give initial conditions. And here in the space, three-dimensional space with coordinate x1, x2, x3, what is written here? It is derivative of the function u in the direction of vector, say, a, depending on x. A has the following component: x2, x1, and 1. So, the equation is therefore derivative of the function u in the direction of vector a equals 0. So we have to find the curves such that at every point its tangent vector is a at this point, a of x, xt. No, it does not depend on t. No, this means that we can anyway write it. And so we have to find the integral curve of this vector field. A is a vector field in the xt space. So our equations of the characteristic is the following: dx1 dt is the first component, which is x2. dx2 dt equals x1. How to solve it? So we can write this the following: vector x is x1, x2. Use the vectors and matrices. Matrix A equals 0, 1, 1, 0. Yes. And x equals x of t equals x1 of t, x2 of t, and dx dt equals a times x of t. Yes, I think you remember all this from the course of ordinary differential equations. Now to solve this equation, we have to find the eigenvalues and eigenvectors of this matrix A minus lambda I determinant equals 0. So determinant of the matrix minus lambda 1, 1 minus lambda is 0. Lambda square minus 1 is 0. Lambda 1 equals minus 1. Lambda 2 equals 1. Now, let's find eigenvectors. A minus lambda yi times vector say E1, it is eigenvectors, equal 0. So A minus lambda 1, lambda 1 is minus 1. So it is 1, 1, 1, 1 times E1 equal 0. No, this means that E1 we can say 1 minus 1. No, or any vector which is proportional to it. Now A minus lambda 2I E2 equals 0. It is vector lambda 2 is 1 minus 1 1 1 minus 1 times E2 equals 0. No, these two lines are proportional, so we say that E2 equals 1 1. We can guess it. So now lambda 1 is minus 1, lambda 2 is 1, and so we can write a general solution x of t equals c1 e to minus t e1 plus c2 e to the power t one more. Okay, e. It is vectors. Vector e number 2. And now, what is e? 1, it is 1 minus 1. X of t equal c1 e minus t 1 minus 1 plus c2 e to the power t 1 1. So x of t equals the first c1 e minus t plus c2 e to the power t minus c1 e minus t plus c2 e to the power t. Now, how to find c1 and c2? We have to solve the equation dx dt equals ax. X of 0 equals x0 equals x1 0 x2 0. So if you substitute here t equals 0, then you have, so x of 0 equals c1 plus c2 minus c1 plus c2 equals x1, 0, x2, 0. So from here we find what is c1 and c2. c1 plus c2 equals x1, 0 minus c1 plus c2 equals x2, 0. If you subtract it, we have c1 is x1, 0 minus x2, 0 over 2. c2 equals x1, 0 plus x2, 0 over 2. And so, after all, what we have, let us substitute it here, x of t equals c1, it is x1 minus x2 over 2 e minus t plus x1, 0 plus x2, 0 divided by 2e to the power t. And here minus x1, 0 minus x2, 0 divided by 2e minus t plus x1, 0 plus x2, 0 divided by 2e to the power t equals, let me express this in terms of x1, 0. x1, 0 e minus t plus e to the t x1, 0 e minus t plus e t over 2 plus x2, 0 minus x1, 0 plus x2, 0 divided by 2. And here x1, 0 et minus et minus e minus t divided by 2 plus x2, 0 et plus e minus t divided by 2. And if you recall the notation et plus e minus t divided by 2 equals hyperbolic cosine of t, and et minus e minus t divided by 2 is hyperbolic sine of t, we have that x of t equals the following. Cosine hyperbolic of t x1, 0 plus sine hyperbolic of t x2, 0 one moment, minus e minus t plus e t, so it is et minus, no, it is okay. Here we have sine hyperbolic of t x1 0 plus cosine hyperbolic of t x2 0. Yeah. So at last we solved this, solved our ordinary differential equation. So if x1 0, x2 0 are is coordinates of initial point x0, then a solution is like this. Now let us recall what it was for. So we had this picture, x1, x2, t. Here we have characteristic x of t, y of t, yes, and t. This is the point x1 0, x2 0, 0. And then solution is constant along this characteristic, which is defined by this solution. And so this means that u of x1, x2, t equals f x1 0, wait, let me write, u of x1 0, x2 0, 0, which is the same as f x1 0, x2 0. So we have to find the for given point x, y, x1, x2. For given point x1, x2, and t here on the characteristic, we have to find this initial point. So this means that we have to solve the following system equation. So x of t equals x equals x1, x2. So from here we see that x1, let me write, cosine hyperbolic of t x1 0 plus sine hyperbolic of t x2 0 equals x1, the first coordinate, sine hyperbolic of t x1 0 plus cosine hyperbolic of t x2 0 equals x2. So this is a system of two linear equations, and let us solve it by the Kramer rule. Let me leave this equation of characteristics. First of all, cosine hyperbolic of t sine hyperbolic of t sine hyperbolic of t cosine hyperbolic of t, if you take determinant of this equals cosine hyperbolic square of t minus sine hyperbolic square of t equals et plus e minus t over square minus et minus e minus t over 2 square equals e to t plus 2 plus e minus 2t divided by 4 minus e to t minus 2 plus e minus 2t 4, which is equal these goals remains it is 1. First of all, and then we have then x1 0 equals determinant x1 x2 t cosine hyperbolic of t equals x1 cosine hyperbolic of t minus x2 sine hyperbolic of t. And x to 0 equals cosine hyperbolic of t, sine hyperbolic of t, x1, x2 equals x2 cosine hyperbolic of t minus x1 sine hyperbolic of t. Yes? And so our we found this initial point, and then solution is the following. So our problem is ut plus x2 u x1 plus x1 u xt equals 0, u of x1 x2 0 equals f of x1 x2, and the solution is by this u x1 x2 0 equals f of what is written here, x1 cosine hyperbolic t minus x2 sine hyperbolic t, x2 cosine hyperbolic t minus x1 sine hyperbolic t. Yeah. So this is a solution. No, depending on what is the function, just substitute it here, and we have solution of the equation. No, okay, let us finish at last this topic of first order equation, and let us go to the next topic. It is the next topic is string equation. So consider the following. In general, string equation u second derivative in t minus u second derivative x equals 0, and let us start from solution on the whole line. U for t equals 0 equals, say, f of x. Ut for t equals 0 equal g of x. Now, solution of this equation is given by the following formula, which you, I think, know by heart. U of xt equals 1/2 f x plus t plus f x minus t plus 1/2 integral from x minus t to x plus t g of y dy. So we have this D'Alembert formula. Depending on what is your function, functions f and g, you will have solution. So I don't know what can be said about this. So let us consider the problem on half line. UTT minus UXX equals 0, x more equal than 0, t more equal than 0. Now we have to give initial conditions. U for t equals 0 equals f of x, ut for t equals 0 equals g of x. It is initial condition. But then we have to define something on the t-axis, where x equals 0. So it is the boundary condition. Now we consider two sorts of boundary conditions. They are either Dirichlet condition or Newman condition. So consider the Dirichlet condition. U of 0t equals h of x. So this is initial boundary value problem for the string equation. Now, how to approach this problem in general? I would beat this problem by parts. So I will set some of this function 0, and then I will solve this with part of these conditions are right-hand side are zeros, and part are ones or two are not zero. So let me do it the following thing. For example, u equals v plus w. So I decompose the function u in two functions, v and w. And they satisfy the following conditions. V tt minus v xx equals 0. So it is also a solution of string equation. V for t equals 0 equals 0. Vt for t equals 0 equals 0. And v for x equals 0 equals h of t. Yeah? So it is one set of conditions. And the other set of conditions for w, w tt minus w xx equals 0, w for t equals 0 equals f of x, w t for t equals 0 equals g of x, and w for x equals 0 equals 0. Now, if you add these two functions, first their sum also satisfies the string equation. Now, the sum of this function satisfies this condition that the sum is f of x, its time derivative is g of x, because here it is 0 and here f and g. And for x is 0, this x value is here h of t, here is 0, so the sum is h of t. And so we beat these two two problems in different ways. So first, for v of x, x t. We know that every solution of the string equation has the form of one function of x plus t and other of x minus t. And we just guess that this function has v of xt equals some function phi of x minus x minus t. Yeah. So this function is constant along characteristics which are parallel to the diagonal x equal t. And let us define it that on the characteristic going through the point, one moment. So we have to divide our plane xt, no, here quarter plane, in two parts by this diagonal. So here we write the point xt where x more than t. Yes, and we write u this function phi of x minus t. So let us have solution which is 0 here, yes, and which is equal to, so if you have the point xt, then the corresponding point on this characteristics through xt here will be 0 t minus x. Yes? T minus x. And so we write phi x minus t let me say t minus x. Phi of s equals h of s, s more equal than 0, 0, s less than 0. Then it is really, so v of xt equals phi of t minus x. It is here. So here this function is a 0. Here this function is a solution satisfying the boundary condition on the t-axis. It is for the function v. Now, if you want to avoid difficulties here, say this function v should be function h, h of t. H of t should be 0 for t equals 0. To avoid no jump on the diagonal of this solution. Now, what about the equation for w? We know how to do it. If the function satisfies this boundary condition, Dirichlet boundary condition, then the best way is to continue this function to the left for negative t as an odd function. Yes? So w of minus x t equals minus w of xt. Yes? And we write, to do it, we continue f and g as odd function. F of minus x equals minus f of x. And g of minus x equals minus g of x. Yeah? So we take the odd function on the x-axis, f and g, and then the formula, we use the general formula of the Lambert solution. And this formula gives us automatically first solution here, and which is 0 on the t-axis because it is an odd function. Yes? Now, to make this all this consistent and to avoid the discontinuity again here on the diagonal, we have to have that the function f is 0 on the 0 at 0. So there should be h of 0 is 0, f of 0 is 0. These are consistency conditions so that our solution is at least continuous. So this is, then you write w of xt equals 1/2 f of x minus t plus f x plus t plus 1/2 integral from x minus t to x plus t g of y dy. So this is solution of this problem. In fact, it gives solution on the whole line for all x, positive and negative, but we just restricted to the positive half line. No, that's it. No, in particular, this V gives us a solution of the following problem. Let me leave only this. So v t minus v x equals 0, x positive, v for t equals 0 equals 0, vt for t equals 0 equals 0, and v for x equals 0 equal sine omega t. Yes? So it looks like this. We have a semi-infinite string and keep its end point in our hand, and the other end is somewhere at infinity. And the string is at rest, and at the initial moment we start moving this tip end point of the string, it produces harmonical motion. Yes, it's so we have this string, and then we start moving it up and down. And so what we have here v of xt equals by this formula sine omega t minus x for t x less or equal than t, yes, and 0 for x more than t. So it looks like this. Something like this. Here is the end point of the string. Yes. So we see how this oscillation of the initial point is spreading along the string. So the say active part grows linearly. There was a famous work of the great mathematician William Hamilton. No, he was one of the greatest people in mathematical physics. It was called How the Light Conquers the Darkness, or Occupies the Darkness. Yeah? So he considered some simplified model of propagation of light starting from complete darkness, and then this light wave propagates. And what I explain here is the simplest model of what is written in the Hamilton's paper. It was a striking example of work. It was its significance is clear right now. Okay, so let me consider one more problem about the string equation. In fact, we spent too much time on string, but in fact this time was spent to introduce some important notions of partial differential equations, so I think it was not completely lost. So I will solve one more problem because it is maybe similar problem may appear in exam. So consider the string equation on finite string u t minus u x equal 0. Here x from 0 to 2, for example. U for t equals 0 equals f of x. ut for t equals 0 equals 0. And conditions, it is 0, it is 1, it is 2. U for x equals 0 equals 0, and u x for x equal 2 equals 0. So we have to give two boundary conditions. Here boundary conditions is Dirichlet condition, and here it is Neumann condition. And what is the function f of x? F of x is the following. 0 between 0 and 1, and 1 between 1 and 2. So it is a function like this. Yeah? No, maybe you asked me why it is too singular. We know that string equation make sense even for discontinuous functions, so I explained it. So we can say modify it a little bit and it will be a smooth function, then we can work with it, and then we can take the parameter epsilon, parameter of modifier, go to 0, and in the limit we have this. So it is what I call the weak solution. And so how to approach this problem? Again, we have to use the reflection method. It is 0, 1, 2. It is our domain of interest. Yes, and so here the function, let me draw it in red. The function is like this. Now from 2 to 4, we continue this function as an even function because here we have a Neumann condition. And from to the left, from 0 to -2, we continue this function as an odd function. Similarly, we continue it here. Also, 4 is a reflection of 0, so here the function should be odd, so it looks like this. Here, -2, -3, -4. So here we have again, it is a reflection of the point 2. At this point 2 we have Neumann condition. So here we have also even continuation like this. And so this way we have, let me say, from say it is -2, it is 2. So this is one period of the function. Next, the function will be continued periodically as a periodic. So the period length of period is just 4. No, one moment. No. It repeats from here, from here to 6, -2 to 6, or -4, -2, -4. Yes, this is the period. So the period of this function is 8. Okay, anyway, so this is the function f of x already continued on the whole line. Let me stay with this function, and then solution is u of xt equals f 1/2 f of x plus t plus f of x minus t. Okay, and now we have to find this function by this formula. So I have to draw a picture, a larger picture. So let me use the whole blackboard. Is it blackboard? No, it's whiteboard. 2, 4, 6, 8, 10. Now I need enough space. Minus 2, minus 4, minus 6, minus 8, minus 10. Okay. Now let me again sketch the function. So here from 1 to 3 it is plus 1. Here it is from minus 1 to minus 3 it is minus 1. Now here it is minus 1, from 5 to 7 here it is plus 1, and here it is anti-symmetrically like this. So you see, this is the graph of the function f extended to the whole line, so that at the point 0, 4, 8, minus 4, and so on, if you reflect relative to this point, we get it is odd reflection, and with respect to the point 2, 6, 10, minus 2, minus 6, minus 10, it is even reflection. And now let me draw the domains where we will look for solution. So, the function is, you see, the function is piecewise constant. So solution will be also piecewise constant. So let us draw the characteristics. Like this. So in fact we need our solution only from x from 0 to 2. So it is this strip. Let me do it more vertical. In this strip, and in this, yes, like this. So first of all, we draw the characteristics through all the points of discontinuity of initial condition. This goes like this, and this goes like this. Okay. No, I'm sorry. They should cross here. And so on. And now let us think. Here from -1 to 1 the function is 0. And so if you draw the characteristic from any point in this triangle, it will be 0. So here u is 0. Here, in this square, x minus t is in this segment where u is f is minus 2. Here is f is 2. So here it is also 0. And the same is here, 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 and so on. Here, one moment. Here it is function equal 1. So if you take the characteristic here, the result will be 1/2 plus 1/2. So here it is 1. Here u equals 1. In this triangle, in this square, one characteristic hits crosses the x-axis here where u is 0, other where u is 1. So here it is 1/2. Here it is 0, here it is 0, here it is 0. Here it is 1. Here it is 0. Here minus, just a minute. No, one moment. 0, here is minus 2, minus, it is minus 1. Here it is 0. And here it is 1 here and 1 here. So it is 1. 0 minus 1, now you see the pattern. Remains to find it here. It is 1/2. Here it is minus 1/2. Here it is 1/2 minus 1/2. Yes, and here we have again 1 from 1 to 2 and 0 from 0 to 1. So this is 1, 2, 3, 4, 5, 6, 7, 8. And now let us draw the snapshots of our solution. So we have to take the segment from x from 0 to 2 and for different t. For t equals 0. We have this picture. It is 0, 1, 2. Let us take t equal 1/2. This is our domain of interest, x from 0 to 2. T equal 1/2. T equal 1/2. We have it is 1, it is 1/2, it is 0. Yeah? 1, 1/2, 0. T equal 1. For t equal 1, it is all 1/2. For t equal 1.5. T equal 3/2. It is here. so from 0 to 1/2 it is 0, 0. Then from 1/2 to 3/2 it is 1/2, and then again 0. Is this. T equal 2. It is 0, 0. This T equal 2. 0. T equal 5/2. 0 minus 1/2, 0. 0 minus 1/2, 0. It is 1/2, it is 3/2, it's 4, 2. T equals 3. Again, it is all minus 1/2. T equals 4. For t equal 4, it is 0. So, no, from this to this it shrinks. Here it is, at this stage it expands, then it will shrink, and then we have 0. T equals 5. For t equal 5, it is 1/2. T equals 6. Again 0. 6. One moment. T equal 4. 0. No. It is 0. It is here minus 1. T equal 5. 1/2. T equals 6, 0. T equals 7. Minus 1/2. And t equal 8, again 0, 1. T equal 8. No, here I did not draw this half integer time moments where these waves are moving. You can do it yourself. So this is a sample of solution of wave equation on a finite segment with different boundary conditions and simple discontinuous initial value, initial condition. No, okay, let's finish for now and see you very soon. Have a good time, bye.